Good morning, dear students. Can you hear me?
Yes.
Okay.
Yes.
So, can you see the whiteboard?
Yes, we can see the whiteboard.
Okay, let's begin. Uh, Last time, we finished with defining two set theoretic operations, namely the intersection of two sets. The intersection gives us all elements of A, which also are elements of B. And as well, we defined the difference of two sets, all elements of A, which are not elements of B. We have stated the following fact. Let's call it lemma 1. For every A and B, the intersection is a subset of A, and A is a subset of the union of two sets, the same for B, and also A minus B is a subset of A, and A minus B is disjoint from B. And now we are going to prove a very useful fact, namely the following one. For every A, B, C, D, for every three, we don't need C, in fact, for every two sets A and B, the following statements are equivalent. So I say that A is a subset of B if and only if the intersection equals what? When A is a subset of B,
A.
the intersection is A if and only if, and dually the union is B. Why this theorem is that important? Because in many problems, you are given with such a condition. Some set is a subset of some other set. But if you wish to use various identities, then you want to reduce this fact to an equality. And here it goes, you can equivalently replace an inclusion by an equality. We shall see the examples. Okay. A proof. If I want to prove that three statements are pairwise equivalent, it is enough to prove three implications from 1 to 2, from 2 to 3, and from 3 to 1. Okay, let's do that. Assume that A is indeed a subset of B. I want to prove that this one equals A. Of course, we know that two sets are equal if and only if each set is a subset of the other one. So this is a standard procedure when proving set equality. The standard procedure is to prove two inclusions. Okay. The first inclusion that the intersection is a subset of A. This follows from lemma 1. So this is by lemma 1. And why A is a subset of intersection. Why A is a subset of intersection. Let's use the definition. We want to prove that every element of A is an element of the intersection. Okay, if X is an element of A, then it is an element of A, clearly, and also it is an element of B. Why? Why is it an element of B?
Because A is the subset of B.
Of course, by our assumption. By the assumption. Okay. That is, X is indeed an element of the intersection. So we have two inclusions which result in equality.
Excuse me, and
Uh-huh.
can we use the previous fact?
Which one?
The can I comment or?
Of course, please.
But no, I can't actually. Okay, the fact that you proved by lemma 1, it's on the left side.
So the first inclusion follows from lemma 1.
Yes,
But
we can use the transitivity of the inclusion and say that A is a subset of A. Isn't it true?
A is a subset of A. And what of it? You need this one. Assume you know that this holds. Of course, A is a subset of A, and the intersection is a subset of the intersection. And what of it? How is it possible to prove the converse inclusion from this one?
Okay, I see.
So I can't see the way to do so. Okay. From 2 to 3. Now, assume that the intersection indeed equals A. Here I need that the union equals B. One inclusion is trivial. B is, of course, a subset of the union. We know that every set is a subset of any union where it is present. So this is by lemma 1. And what about the opposite direction? Why this is a subset of B? Let's prove. If X is a subset of the union, then by the definition, X is either an element of A or it is an element of B. Is it clear?
Yes.
Okay. But we know that A equals the intersection. That is, X is an element of the intersection, or X is an element of B. But we know, of course, that any element of the intersection, say by lemma 1, is an element of B as well, by definition. So X is an element of B or X is an element of B. That means that X is an element of B. So I think this is quite clear as well, isn't it? Any questions? No. Okay. And the last step, the last implication, it is also very easy. Assume that the union indeed equals B, and I need that A is a subset of B. Now I need just one inclusion. It is very easy. A is a subset of the union. This is by lemma 1. And this by assumption equals B, of course. I know that if they are equal, of course, there is an inclusion. Inclusion is transitive, whence A is a subset of B. Is it clear?
Yes, it's clear.
So, dear students, these two statements are equivalent. It is very, very useful. And in fact, this lemma, we shall see it later, is similar to the following fact. N divides M if and only if the greatest common divisor equals what?
N.
Surely. Or equivalently, the least common multiple equals
M.
Or another fact of exactly same form. N is less or equal than M. These are numbers, say naturals. N is less or equal than M if and only if the minimum equals N. Or equivalently, the maximum equals M. So you see that inclusion plays the same role as minimum or the greatest common divisor, and union plays the same role as the least common multiple or maximum. We will develop this analogy later. Is the similarity clear? That is, there is some similarity. A is less or equal than B if some function of these two equals A, if and only if. Dear students.
Yeah.
Okay, there is something interesting. But of course, we should elaborate on that later. We'll do that later. And now, let's define one more interesting operation. Assume that A is a subset of some U, where U is fixed. What does it mean, fixed? Fixed, that means that it is known from the context, and we don't want to mention it explicitly every time. Then such U is called the universe. Of course, it is not, no way, it is not the set of all sets or something like that. It is just the set such that every set in our context is a subset of it. So something like when you are speaking about subsets of natural numbers, so as you can take the set of all natural numbers or something like that. Okay, then the set U minus A is called, it is called the complement of A, that is 2U. The complement means in Russian дополнение. And we'll use the following symbol: A bar, A with a bar, A overlined. This is our complement, U minus A. Clearly, A bar, clearly A minus B if If A and B are subsets of U, then A minus B, all elements of A which don't belong to B, this is the intersection of A and the complement of B. Is this clear or not? If we have two subsets of some U, what is A minus B? This is just the intersection of A and the complement of B. The complement of B. Is it clear?
Yeah.
Of course, it is quite trivial. And now let's state the following important theorem, which gives us so-called set algebra identities. You have to memorize these identities. For every U, for all A, B, C, which are subsets of U, we have the following. The intersection of two sets equals the intersection of the same sets in the opposite order. Of course, this identity does not depend on the fact that A, B, and C are subsets of U. Of course, for every two sets, you can take their union as such U. So there is no problem. And likewise, the union is also commutative. The intersection is associative. It enjoys the associativity property as well as the union. What else? The intersection is idempotent. That is, if you intersect a set with itself, it does not change. The same for the union. Absorption laws, so-called absorption laws. What else? What else? Of course, here we have some problem. Not that. This way. Of course. 5. Double negation. Double complement. The complement of the complement equals what?
A.
The original set.
Of course. The distribution laws. The intersection with a union equals the union of two intersections. And dually, the union of A and the intersection equals the intersection of two unions. 7. De Morgan's laws. De Morgan's laws. The complement of the intersection equals
The union of complements.
Of course, that's it. And the union of the complement of the union equals the intersection of complements. Number 8, constants. The intersection with a set of a set with the empty set equals,
Empty set.
of course, the union
A.
the union with the universe. You know, A is a subset of U, so by the previous lemma, the intersection equals
A.
Just A.
and the union equals, of course, U. The complement of the empty set equals
Universe.
the universe. The complement of the universe is the empty set. And the last one, the intersection of a set with its complement is empty. They are disjoint. And the union of a set with its complement yields the whole universe. I think that these laws are familiar to you. Am I right?
Yes.
Yes. Seems like.
Should we prove them? Probably we want to prove one or two identities here. For example, let's prove one of the absorption laws, because probably they are not that familiar to you. Okay, say I want to prove that A equals A intersected with the union. It's very easy to prove it. What is the main idea? The main idea is use the definitions. What does it mean? That X is an element of this intersection. Two sets are equal, you know, when every X is an element of one set, if and only if it is an element of the other one. That means that X is an element of A and X is an element of A, or X is an element of B. Of course, here we have two cases. Either X is an element of A and X is an element of A, or X is an element of A and X is an element of B. That means that X is an element of A, or but of course this is not needed. This is not needed. Okay. Just see. X is an element of A and X is an element of A, or X is an element of B. Do you agree that this is enough for X to be an element of A? After all, here we have a conjunction, and from a conjunction, of course, it follows that every member of that conjunction is true. Is it clear? Dear students.
Yes.
And for the converse direction, you know that from alpha, it follows that alpha or beta. And of course, from alpha, it follows alpha. From this one, it follows that X is an element of A or X is an element of B. And of course, it follows that X is an element of A. That means that from this one, it follows that both statements are true. So I am just reducing my statement to a statement about logical operations. So the main idea is that my set theoretic operations just mimic logical operations, logical connectives. Is it clear?
Yes.
Yes.
Do we need to consider another identity? Or is it quite clear?
Well, I think it's clear.
Okay. So the main idea is as follows. Use the definitions and the properties of logical connectives. Where from can you infer these properties? Of course, from truth tables. This is always true. This is a tautology. Why? You may just make a truth table and check. Okay, let's see some applications of these identities. Assume that I want to prove the following statement. For every A, B, and C, A minus B minus C equals A minus B union A intersected by C. How is it possible to prove it? Of course, I can use the definition, but it is not very elegant way to do so. Let's use the identities. At first, let's introduce some universe. Let U be the union of these three sets. By the way, you know that A union B union C is the same set as A union B union C. So the place of these brackets just does not matter. So you may omit the brackets, assuming that they are, in fact, they are somehow placed, or better, they are placed this way, left associative. Okay, let U be the union of all three sets. Clearly, this can serve as a universe, and we may have the following. B minus C is just B intersected by the complement of C. Is it clear?
Yes, it is.
So the left-hand side is just A intersected by what? By the complement of this set. And now we may easily use our De Morgan's law. The complement of the intersection is
The union of complements.
the union of the complements, of course. Double complement does nothing. So then I'll apply distributivity and obtain something like that. It is A minus B union A intersected by C. Is it clear?
Yes.
Of course, I'm freely substituting a set. I'm freely substituting a set for an equal one, according to my substitution principle. That is, in every context, equal sets behave identically. And now let's see some application for our lemma, which replaces set inclusion by equivalence. another statement for every three sets A, B, C. If A is a subset of C and B is a subset of C, then the union is a subset of C as well. Of course, I may consider elements, but I don't want to do so. Now I'm given with these two inclusions, and I may rewrite them the following way: C equals the union of A and C, and also C equals the union of B and C. And I need that the union of these two sets equals C as well. How is it possible to do so? Okay. From the first one, C equals A union C. This is my first assumption. By the second assumption, I can replace this copy of C by B union C. And now I'll apply associativity in order to regroup these sets. So this is the thing I want. Is it clear?
Yes, it is.
Yeah,
Yeah,
but
and
it seems like you're missing the last step, like to turn.
Which one?
Like we actually need the A union B is a subset of C, and we have to turn the last one. Since A, we have a theorem about it.
No, these two are equivalent.
Yes, and that's the
Because
theorem I'm talking about. Yes.
likewise, I have used the same lemma here when I have replaced when I replaced this conjunction by the conjunction of two equalities. But anyway, is it clear?
Yes.
Okay,
Yes.
let's move on. So far, we have seen that the concept of ordering of elements is not reflected by our concept of set. So there is no order of the elements of a set. These two sets are the same. But anyway, ordered pairs or triplets and so on are very important in mathematics. For example, if you consider the coordinates on the plane, you know that 0, 1 and 1, 0 are distinct points. So how is it possible to model? How is it possible to model ordered pairs, ordered so-called tuples, that is pairs, triplets, and so on, using sets? Is it possible? In fact, it is. I want to model an ordered pair via sets. Interesting. Let's do that. By definition, for every two A and B, I'll introduce the following set. It is quite artificial, of course. It is artificial. But anyway, it will work. Let's call the ordered pair of A and B just this set. By the way, is it possible that this set is a singleton?
When A and B are equal?
Of course. What if A equals B? Then the pair equals what? This set, which is just this one. That is the singleton of the singleton. The following statement holds. Let's call it ordered pair equality criterion. For every A, B, C, and D, these pairs are equal if and only if. So please, what do you think about it?
A equals C and B equals D.
A equals C and B equals D. So as a corollary, I say that the order does matter. Why? When is it possible that AB equals BA? I see if and only if A and B are the same. Is it clear?
Yes.
How is it possible to prove this easy theorem? Okay, let's prove it. From the right to the left is trivial. We know that equal sets behave identically. So you may just replace A by C here and B by D. Is it clear?
Yes.
And now assume that these two sets are indeed equal. What does it mean? That means that this set AB equals this one, CD. I need A being equal to C and B being equal to D. It is quite clear. Ha! By the way, from my assumption, I see that, say, the singleton of A is an element of this set. Do you agree?
Yes.
Why? Because it is an element of the left-hand side. Hence, it should be an element of the right-hand side. Then, excuse me. I need this fact. Okay, that means that the singleton of A is either the singleton of C or this set. Is it clear?
Yes.
It is.
Yes.
Ha! But C is an element of this set. C is an element of this set. That means that in both cases, C is an element of the singleton of A. The singleton of A has the only element A. That means that C equals A. So my first my first equality has been established. Is it clear?
Yes, it is clear.
Okay. And now let's consider this set. It is it's also either this singleton or this set. So we have two cases. We have two cases. The first case is when this set equals C, and the second case is when this set equals this one. For the first case, I know that B is an element of this set, hence B must be an element of the singleton, hence B equals C. So in the first case, B equals C, while C equals A. We know that C and A are the same. And what about D? If I consider this set, I know that it is either the singleton of A or this set. So C, D, this unordered pair is either this set or this one, A, B. So what can one say about D? D equals A, which is the same as B, or otherwise D equals A, which is the same as B, or D equals B. So anyway, D equals B. So in the first case, both equalities hold. Is it clear?
Yes, and actually they're all equal.
Of course, of course.
Yes.
But the second case differs. In the second case, I have these two. And now let's look at D. D is either B or A. Do you agree?
Yes.
If D equals B, we have proved what we want. Assume that D equals A, but we already know that A equals C. D equals A equals C. Okay, but then our AB equals what? It equals D, because D and C are the same. So it is a singleton of D, whence D is an element of the set, or better, B is an element of the set, that is B equals D. And of course, all four sets are equal to each other. Is it clear?
Yes, it is.
So we have some case analysis, which shows that if these sets are equal, then A equals C and B equals D. I think it is not very complicated. In general, we don't want to know the inner structure of this pair. The main fact about this pair is this one, that two ordered pairs are equal if and only if their respective parts, their coordinates, let's call this coordinates, the coordinates of our pair, if their respective coordinates are equal. Okay. And now let's group all pairs where A comes from A, from X, and B comes from Y. Let's group all such pairs together. In order to do that, let's make the following observation. You know, by definition, we have this thing. Okay. Let A and B be elements of some common X. Then what can you say about this singleton? It is a subset of X, while this one is a subset of X as well. Do you agree? Ladies and gentlemen,
Yes.
Totally.
Yes. we agree.
Actually,
if they are subsets, they are, of course, elements of the power set, of the set of all subsets. These two are elements of this set. That means that if we group them together, we will obtain a subset of P of X. Just formula. If we have two elements, you may group them together and you will obtain a subset. And my last step is more scary. That is, the ordered pair of these two sets is an element of what? Of P, it is a subset of what? Of this thing. As it is a subset, then it is an element of P of X. Aren't you afraid of this?
Can you repeat, please? I didn't
Okay,
get it.
let's repeat. Assume that A and B are elements of X. Then both these sets are subsets of X. Hence, each set is an element of P of X. Is this clear?
Yes.
What if we group them together? Then we will obtain what? A subset of P of X. Why not? Every element of this set, either this one or that one, is an element of P of X. But in general, if alpha is a subset of beta, then alpha is an element of the set of all subsets. Just think abstractly.
Oh, okay. I get it. Thank you.
Okay. So we see that the ordered pair is an element of this set. We have found a set where our pair belongs to. And after this step, we may freely construct the set, which is called the direct or Cartesian, from Cartesius or Descartes, who was, a classical mathematical author, direct or Cartesian product of two sets. What is it? Formally, this is the set of all elements Z of the union of U and B of this set, which is a pair. So Z is a pair of some A from A and B from B. Or in symbols, there exists A in capital A, there exists B in capital B, such that Z is just their pair. So this is the set of all possible pairs. Is it clear?
Yes.
Less accurately, I may write it the following way. The product is just the set of such pairs. But it is less accurately. More precisely, this set is defined this way. By the way, this set indeed exists. Why? Because it is constructed according to our principles. We know that the fourth principle says that there is a union. The third principle says that there is a power set, the set of all subsets, and then we apply our second principle of subset specification. So this set is constructed according to our principles. Is it clear?
Yes, it
Yes.
is clear.
Okay. And the main fact about this set is as follows. It might seem very easy, and it is very easy, but it is still important and not that obvious. For every x and y, the pair of x and y belongs to this product if and only if x belongs to A and y belongs to B. Why is it so? Okay, let's prove it. What does it mean that x belongs to this set? According to the definition, that means that there exists A, there exists B, such that A is an element of capital A, B is an element of the capital B, and our pair XY equals this pair. Is it clear?
Yes.
This is strictly according to our definition. Strictly according to our definition. But now we want to apply our criterion. So pair equality criterion. When two pairs are equal, two pairs are equal when?
When x equals A and y equals B.
This is the critical part. We need it. That means that every set might be expressed as an ordered pair, no more than one way. So now I see that A is an element of capital A and X equals A. We know that equal sets behave identically. We know that by our formula by the axiom of equality. By the axiom of equality, if A, little a is an element of capital A and X equals A, that means that X itself is an element of A, and likewise Y is an element of capital B. Is it clear?
Yes.
And for the opposite direction, if X is an element of A and Y is an element of B, then clearly there exists A and B such that A is an element of A and B is an element of B, and our pair equals their pair. That's clear. It's trivial. What should I take as A? Dear students, what should I take as A?
Wait. What was
Take
that?
X, take X. No,
Yes.
of course. This one is true. And also, then we know then X and Y are elements of the union. As X is an element of A and Y is an element of B. Then we know that they are pair according to our remark. According to our remark, their pair is an element of P of the union. But these two conditions, in fact, define the set of, define the product. The product is a set of all elements of this Carey set such that there exists A and B. And for our pair X and Y, I see that our pair belongs to this set. And also there exists A and B. By the definition, my pair belongs to the product. Is it clear?
Yes.
Okay, let's memorize this statement. It is very intuitive. A pair is an element of A times B. They can they read it A times B or A product B if and only if X is an element of A and Y is an element of B. There is no way to express such a pair any other way. So what does it mean? What if I want to consider a product of 3 or more sets? In general, and we shall prove it, A times B is not equal to B times A. It is quite clear. Why? What if you take the following product? It consists of exactly one pair. Is it clear?
Yes.
And here we have this pair. They are not equal. Why? Because this pair is equal to this one. This would mean that 1 equals 2, which is false. So in general, A times B is not the same as B times A. And also, it is not associative. So if I have such a product, I want to indicate, I need to indicate some places for parentheses. Let's make them left associative. And in general, if I have n sets, where n is at least 2, I'll do this thing. Is this convention clear?
Yes.
Okay. And this allows me to make the last step, namely to introduce the so-called Cartesian power. Cartesian power. I want to say that a to the power 0 equals what? By the way, a natural number to the power 0 equals?
1.
1.
Of course. So here I need, please use your intuition, a set with how many elements?
One
No.
element.
What is the simplest set with one element?
The set of
Uh,
empty set.
An empty
Yes.
set?
The singleton of the empty set, of course. A to the power 1 equals, use your intuition,
Just A?
A itself.
A itself, of course. That's natural. And if n is at least 2, a to the power 2 is what? It is a product
Of all.
of n copies of A. So what is Cartesian power? Say what is now please give me 2 or 3 minutes to finish that presentation. First of all, do you agree that for every n which is at least 1, a to the power n plus 1 is just a to the power n times a? Is it clear?
Yes.
You know, here we have left associative brackets. Okay. Another definition. Let A1 and so on be some sets. I call this structure A1, A2, AN. Please switch your microphone off. Please switch your microphone off or I'll do it for you. Thank you. So I'll introduce such a symbol, A3 and so on, AN. For example, A, B, C is just the pair of the first two and C. I call this one the n-tuple, not tuple, but still tuple, the n-tuple of A1, AN, of sets, of these sets. Is the meaning of this thing clear? What is a tuple? A tuple is a generalization of a pair. For example, what is a triplet or 3-tuple? It is a pair of the pair of first elements and the last element. Is it clear?
Yes.
Clearly, X is an element of this product if and only if it is a tuple. That is, there exists A1 from capital A1 and so on, such that X is a tuple of these sets. Why is it so? Because here we have left associativity for brackets, and here we have the same. In particular, X is an element of the Cartesian power if and only if there exists some A1, AN, such that all these elements belong to A, so that X is a tuple. For example, x is an element of z to power 4 when? If and only if you have 4 integers such that your x is such a tuple, such an ordered pair. Is it clear?
Yes.
And my last remark deals with equality of tuples. Two tuples are equal when? If and only if, so please continue.
A1 equals B1 and so on, and
And so
AN.
on. AI equals BI for each I.
Yes.
Of course, how is it possible to prove it? Just apply the criterion for pairs. How many? In fact, n minus 1 times. Let's do that for, say, 3. When this one equals this one, B prime, C prime. That means that, you know, this is just this set, and this is this one. So this is exactly when this takes place, exactly when these two pairs are equal, and C equals C prime. That is, here we have a conjunction, A equals A prime, B equals B prime, and C, excuse me, and C equals C prime. Both steps are by the criterion, by the equality criterion for pairs. Is it clear?
Seems inductive.
Of course, it's possible to prove it formally by induction, but there are some formal difficulties here. There are some formal difficulties here, which arise from the fact that we need a recursive definition for our tuples, for our powers, and such formal recursive definition needs another set construction principle. So these things are somewhat complicated, and we don't want to consider them. So in general, now we up to now we have formally defined Cartesian products of multiple sets, and in particular we know what does it mean. A to the power 3, say that is A times A times A, which is a set of all ordered triplets of the elements of our set. Is it clear?
Yes.
And now we are not afraid of, say, R to the power 3, which is a set of all ordered triplets of real numbers, which might be identified with the points of a space, of Euclidean space. You know, the coordinates and so on. So now we are able to introduce coordinates and deal with them. Any questions, dear students? Dear students?
No questions.
No questions.
No questions. Was it clear enough?
Yes.
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 Yeah,
Yes,
it
it
was.
was.
So thank you. If you still have any questions, you may of course ask them in our group, and Also, please consult to my lecture notes, where all these things are transcribed, I think, in quite a clear way. Thank you. Thank you, dear
Thank you.
students.
Bye.
Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thanks, thanks.
Probably we have some questions in our chat. So thank you. No, that's clear. No questions. Okay, thank you. Thank you.
Sorry, one question.
So please.
About your lecture notes. Firstly, I cannot find such topics in your lecture notes. In your lecture notes.
See lectures 2 and 3.
It's 2 and 3.
Lecture 2, namely.
Okay. I've been looking on 7 and 8. And also one question about our test. Can we use your lecture notes on our test? Yeah.
Of course you can. Why not?
Okay, thank you. Goodbye.
And your personal notes are also allowed.
Okay, thank you.
Thank you. Goodbye.
Goodbye.
Will there be a record of this lecture, or you didn't?
I hope that it will be. It should be, at least.
I see. Thank you.
Thank you. Goodbye.
Евгений Владимирович, у меня вопрос.
Ага.
Вот мы когда с вами определяли, как это?
Декартовое произведение.
Да. Мы с вами сказали, что кортеж там из двух элементов, это множество из...
определение пары.
Да, определение
кортежа.
пары.
Пожалуйста, вот оно.
Вот, да. И мы с вами там, ну, как бы сказали, что вот это вот... рисовать нельзя. В общем, вот это вот, то, что мы определили через множество именно, вот, оно у нас, каждый элемент этого множества принадлежит P от X. Вот оно пониже, да. А потом мы сказали, что множество из вот этих вот двух множеств, оно как это, subset
является подмножеством,
да.
P of X, да, конечно.
Да, а потом мы с вами просто, ну, как бы, не знаю, обратную замену сделали и сказали, что это принадлежит P от X.
Ну, смотрите, у нас есть общий факт, что ведь P от чего-то это множество всех подмножеств.
Это понятно, да. У меня вопрос. А нельзя ли эту цепочку бесконечно продолжать и получать постоянно P от X, P от P, ну и так далее, в общем?
Ну, в известной степени можно. Смотрите, если у меня А попадает в X, то даже проще, не надо нам пару. Синглетон А попадает в P от X. Синглетон А попадает в P от X. Ну и так далее. Ну,
это разве не противоречит вот Axiom of Foundation, что мы не можем бесконечно?
Нисколько. Смотрите, у нас получается цепочка, но она она бесконечная, но она возрастающая.
Да, там же было для убывающих, точно.
Вот возрастающая сколько угодно. Не может быть бесконечно убывающей цепочки.
Я понял.
Вот вы не можете по структуре множества идти вниз, в глубину, бесконечно долго.
На высоту я могу.
Да, выше, в другую сторону, пожалуйста. Вы можете усложнять множество неограниченно, но упрощать вы его неограниченно не можете.
Я понял. Спасибо большое.
Да, пожалуйста.
Спасибо.